Imagine a material so light that it can gently rest on a soap bubble, yet so strong that it can support more than 1,000,000 times its own weight. Sounds like science fiction? Well, this innovation is already a reality. Scientists from the University of Toronto, led by engineer Tobin Phillitter, have developed a nanomaterial that could revolutionize everything from aerospace to medicine. And the most impressive part? This structure wasn't designed by a human, but by artificial intelligence. In this video, we'll explore how this technology was created, its potential applications, and how it could change the future of material engineering. The problem with traditional nanomaterials. Nanomaterials have been studied for decades due to their incredible mechanical properties, combining extreme strength with lightweight properties. However, their biggest limitation has always been structural design. Many of these materials, while theoretically strong, had geometric patterns that didn't distribute stress efficiently, making them prone to breaking. But what if there was a way to find the perfect shape to make these materials nearly indestructible? That's where artificial intelligence came into play. The AI revolution in material design researchers developed an artificial intelligence algorithm capable of identifying the optimal geometric configuration for a nanomaterial. The material chosen for this experiment was pyrolytic carbon, a type of carbon obtained through the thermal decomposition of other substances. With this base, the AI analyzed millions of possibilities, and after countless simulations, it found the answer: a nanolattice, a structure resembling a microscopic network, so efficient that it combined the strength of steel with the density of styrofoam. The manufacturing process. 3D printing and pyrolysis. Once AI discovered the perfect structure, scientists moved on to the production phase. But creating something so small and detailed required extreme precision. To achieve this, they used nanoscale 3D printing, crafting the nanolattice structure with high accuracy. However, the real secret came afterward. Through a process called pyrolysis, all unnecessary substances were burned away, leaving behind a structure made of pure carbon. The result? A material capable of withstanding immense pressure while remaining incredibly lightweight. The possibilities are endless. Now, think about all the applications for this new material. Lighter and more fuel-efficient cars, rockets that require less energy, ultralight and durable medical prosthetics. The possibilities are virtually limitless. This could be the first step into a new era of material engineering, where AI and nanotechnology work together to create structures that once only existed in science fiction. Vibranium may not exist outside of movie screens, but this new carbon, nanolattice, might be the closest thing we have to a super strong ultralight material. And the most exciting part? This is just the beginning. With the advancement of artificial intelligence and 3D printing, who knows what other revolutionary materials will be created in the coming years? Plastic pollution is one of the biggest environmental crises of our time. Every year, millions of tons of plastic waste end up in landfills and oceans, taking centuries to decompose. But what if we could accelerate this process? What if we had an enzyme capable of breaking down plastic quickly and efficiently? Until now, nature had no solution for this. There was no enzyme specifically evolved to degrade synthetic plastics on a large scale. However, artificial intelligence has just changed the game. Scientists have successfully designed an entirely new enzyme capable of digesting plastic, a feat that would have been nearly impossible without AI. In this video, we'll dive into how this revolutionary enzyme was created, why traditional methods failed, and how AI-driven protein engineering could transform the future of recycling. The challenge of breaking down plastics are made up of strong chemical bonds that make them durable, but also incredibly resistant to degradation. One of the most common plastic types, PT, polyethylene terephthalate, contains ester bonds, connections between molecules that are stable and difficult to break. While some naturally occurring enzymes can degrade ester bonds in biological materials, they were never designed by evolution to target plastics. This is where synthetic biology and AI came into play. Scientists needed an enzyme that could recognize, bind to, and efficiently break down plastic molecules without getting stuck or becoming inactive after a single reaction. How AI designed a plastic digesting enzyme. Instead of relying on trial and error, researchers used a combination of two powerful AI models, RF diffusion and placer. First, RF diffusion generated various protein structures based on the known configurations of ester-breaking enzymes. These structures were then tested for their ability to bind to plastics. However, most of them failed. Out of 129 AI-generated enzymes, only 2 showed any activity. That's when placer came into the picture. This second AI was trained to refine enzyme structures, ensuring that they could adopt multiple configurations necessary for breaking down plastic efficiently. By combining the two AI systems, researchers dramatically improved the number of working enzymes, eventually creating one that could break down PET. The breakthrough. A fully functional enzyme. Despite these advancements, an unexpected problem arose. The enzymes were able to break one ester bond, but they often got stuck, leaving part of the plastic molecule chemically attached to the enzyme itself. This meant they weren't true catalysts, as they couldn't continue breaking down more plastic molecules. To solve this, scientists ran additional AI-driven refinements, allowing the enzyme to transition between different states required for continuous catalysis. The result? 2 highly efficient enzymes, nicknamed Super and Win, which could complete multiple reaction cycles, effectively digesting plastic into its base components. The future of AI-designed enzymes. This achievement marks a turning point in synthetic biology and environmental science. With AI, we're no longer limited to the enzymes found in nature. We can now design entirely new ones with capabilities never seen before. This could mean future enzymes capable of degrading even more types of plastic, breaking down microplastics in the ocean, or even capturing carbon dioxide to help fight climate change. Imagine a world where AI-designed enzymes turn plastic waste into valuable raw materials, making recycling far more efficient and sustainable. AI has just created a tool that could revolutionize plastic recycling forever. Instead of waiting centuries for plastics to degrade, this new enzyme could break them down in days. And this is just the beginning. With continuous improvements in AI-driven protein design, we could soon see enzymes that tackle even more environmental challenges. What do you think about this breakthrough? Could AI be the key to solving our plastic crisis? Let us know in the comments, subscribe for more updates on cutting-edge technology, and I'll see you in the next video.